Welcome to this first video on the Newton-Cotes integration technique. By the end of this video, you will be able to calculate integrates using the rectangle method. So we talked about what the integral really represents geometrically, right? The integral of a function f of x from a to b is the area underneath the curve f of x going from a to b. Now, the rectangle method approximates this area by a rectangle. And the height of that rectangle will either be the function value at the beginning of the interval, so f of a, or the function value at the right end of the integral, which would be f of b. So if we're using the left function value, f of a, right, we have this shown area that is supposed to approximate the true area underneath the curve. And we can calculate this rectangle area by the function value, f of a, times the width of this rectangle, which is b minus a. If, on the other hand, we use as a height the function value at the right end of the integral, so we would use f of b, then the rectangle area would be f of b times the width, which is still b minus a. So if f of x is monotonically increasing in this interval from a to b, as is shown here as an example, you'll notice that this first rectangle, f of b times b minus a, underpredicts the true area underneath the curve, whereas that right edge rectangle, f of b times b minus a, will overpredict the area underneath the curve. Now, can we improve the rectangle method itself while still using either the left or the right as the height of the rectangle? So how about dividing that interval from a to b into subintervals? Let's divide it into uppercase N subintervals. And then we're going to apply the formula to each one of these subintervals. And then the final integral from a to b will just be the sum of the values that we have found from each one of the subintervals. So then the overall integral from a to b would be, well, the area, the rectangle area, from the first subinterval, which if we use the left function value would be f of x1 times the width of this subinterval would be x2 minus x1. Now we add to it the area of the second subinterval rectangle, which would be f of x2 times the width x3 minus x2. And then we add to it, right, we keep on going to one interval after the other. Let's go to the ith subinterval. The height of this rectangle would be f of xi. Its width is xi plus 1 minus xi. And then we have a whole bunch of additional subintervals to go through. And let's go to the very last subinterval. That's the subinterval from xn to xn plus 1. There the height would be, or the height of the rectangle would be f of xn. And the width is xn plus 1 minus xn. Right? I've divided the interval from a to b into n subintervals. And having n subintervals means I have n plus 1 total points. Okay, so let me look at this here and try to compact that into one formula using a sum symbol. We'll see here that we have the function to be evaluated at x1, x2, all the way to xn. And there's a sum, right, that we add up these individual terms. So this, let me write this as the sum where the index I goes from 1 to n, right? The first term has an x1, the last term has an xn. So then I just need to copy the formula that I found for the ith subinterval into this. So it's the sum I equal 1 to n of f of xi times xi plus 1 minus xi. Now, if all the subintervals have the same width, meaning that all adjacent points are just the distance h apart from each other, then I can shorten this formula and approximate the area underneath the curve by the sum of all the function values from the first to the next to last point, so the nth point, and then multiplying this entire thing by h. I can move that outside of the sum. Let's do an example for this. I'm going to integrate the following data set here using the composite rectangle method. And I've copied over the formula here again for the composite rectangle method. So the formula says that the approximation of this integral of this function is simply h. Now what's h? If I look at this data here, the spacing between adjacent points in the x direction, that's just 1. Okay, so h is 1. So the formula would be 1 times the sum from I equal to 1 to n. So what's n? N is, let's see how many intervals. N is the number of intervals. How many intervals do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals. So 10 intervals. All right, so let me just write here once at least what the I values are. This is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. This is the 11th point. I have 10 subintervals, so therefore I have 11 points. Always 1 point more than the number of subintervals. All right, so now I need to do the sum from 1, so from here, all the way to n, which is 10. So I have to sum up all these function values here. So sum up of all the f of xi is equal to 1 times, let's sum them up, 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81. It's important, common mistake in the rectangle composite method, we do not sum over that last entry. It's not the sum over all data points. If we're using the height of the rectangle, the left value, we will sum starting from the first value to the next to last value. If the composite rectangle method would be formulated for the right bound height of the rectangle, then we would sum from the second value to the last. But here the formula is for the left height. So we have to stop here. We can't include the last data point. Okay, so if you sum all of these up here, you'll find this is 285. It's the approximation to the integral. Thank you for watching.